In this final section, we will appropriately talk about maintenance and retirement. The process of software maintenance is a very involved process, and if you think about it, software will spend a lot of its lifetime in maintenance. It may take us a couple of years to develop, and the software may be in operation for 10, 15, 20 years. So maintenance is actually a big part of the life cycle. We will only present here a very introductory outline view of the topic, but be aware that this can be a very involved process. So we'll continue with our V model, and we're reaching now the step called maintenance. In the beginning of this section, in the next half of the section, we're going to briefly touch on retirement. The standard IC 62304 has a life cycle model for maintenance, as we mentioned before, back in week 5. This is a life cycle for software development. The way it converts to maintenance is that 2 sections get replaced. So 5.1 and 5.2 here get renamed or get changed. So 5.1, instead of becoming development, it becomes maintenance. So development planning becomes maintenance planning, and the requirements for development become modification analysis, and that's fundamentally all that changes. Other than that, the process is identical to developing the software. We have now established what our user needs theoretically, but now we have the maintenance needs, the bug reports that go in, and we have to modify the software. So what are the steps involved in maintenance? We have to establish a maintenance plan. We have to do a problems and modification analysis. This replaces the requirements analysis in the original software design. We have to implement the modifications. We have to test them and repeat all those processes that we did when the software was originally developed. The process of maintenance will continue. We have to have procedures, and this is fundamental, for receiving, documenting, evaluating, resolving, and tracking any issues reported by the users, whether external or internal, and this includes increasingly critically cybersecurity issues. And then we need to establish a process for acting on such reports. We need to determine whether this is an issue or not. We need to evaluate this for risk, and if necessary, we have to make changes. And especially when it comes to cybersecurity, this process has to be reasonably quick. There's a goal to provide updates for cybersecurity within a very short period of time, 90 days or something of that order. So anytime we get a report, we have to evaluate it, we have to document that we have received a problem report, we have to analyze whether this is a mistake on the part of the user, in which case maybe it's a matter of user training, or whether it's an actual problem in the software itself. And then we have to figure out how to prioritize fixes, how urgent this is. Is there a workaround with the current software, just avoid this piece? Or does this require a fundamental change to the software and a new release? And is this a small enough change that we can just update it, or is this a major change that may need to go back for regulatory clearance again? Maintenance, of course, we have to worry, as always, about risk and safety. We have to evaluate any problem reports that relate to safety. This is critical. And this is what part of the failure of the Thera case goes. They got serious accident reports and they did not evaluate the problem seriously. Any requests for changes need to be evaluated carefully for the effects they have on the software and any external systems. And users often fail to appreciate that very small tweaks may require massive changes. This is a common problem. All I want is this additional button, but this additional button may require massive changes to the underlying code. Change requests need to be evaluated and approved, and changes must be communicated to both the users and the regulators as appropriate. And finally, we need to also be able to report to the users new vulnerabilities. So what I mean by that is the following. In the context of cybersecurity, let's assume that a software uses a particular library for a network interface. If we now discover that that library has a vulnerability, or our own code has a vulnerability because of the way it was coded, and this is communicated to us, or we discover it in some way, we need to report this to our users, to the hospitals. There's this vulnerability, maybe this has some workarounds, this is things to watch out for, while we develop a fix to that vulnerability. And maintenance is a massive source of risk. If you remember from the earlier discussions, maintenance and software updates can be a major source of problems. The original developers of the software are gone, and new software developers need to make changes to existing code. And this is by far the hardest job in software development. What separates the experienced software developer from a beginning software developer is how they handle legacy code. Can you read somebody else's code, hopefully somewhat well documented, often not, make sense of it, understand it enough so that you can identify the problem and fix it. This is where experience comes into play, And this is a matter of requires significant practice. It is a lot harder to maintain somebody else's code than to write something from scratch. And this explains in many ways why the old 80-20 statement we've made many times, that 80% of the problems with software, according to that FDA study, happen due to updates, is part of maintenance. Because often the people who do the maintenance are not the people who wrote the original code. And this is a tough challenge. In my experience, when I revisit code that I have written 15, 20 years ago, and I look at it, it's often hard for me to understand what's going on in the code, and I wrote it. Imagine if you're looking at code that somebody else wrote with a very different coding style, and often using stuff that may appear obsolete to you because this was written 15 years ago. And so they're using an older style of programming that you may not have been taught, but you still need to understand, appreciate what's going on, and figure out what to do. And of course, this, by definition, puts a premium on writing clean, easy-to-read code, avoiding unnecessary complexity, because your code is written to be read and fixed later. It doesn't just have to work now, it needs to work for the life cycle of the software, for the entire lifetime, and the maintenance process is critically dependent on this type of thing. And once we're done with maintenance, we maintain our software for a number of years. Eventually, our software comes to an end. And this is the retirement process. So let me show you an example. On April 8, 2014, you see this announcement from Microsoft. After 12 years of support for Windows XP ended April 8, 2014, Microsoft will no longer provide security updates or technical support for this operating system. It is critical to migrate now to a modern operating system. So at some point, even Microsoft, which is famous for supporting software for a very long period of time, stops updating software. And so what they do is that you know ahead of time. We know now, this is the summer of 2020, that Windows 10 will be supported for another 5 years. This is your warning that the clock is starting, and over time you need to make plans to move away from that piece of software to whatever next comes up. So why do we stop supporting software? First, the software becomes obsolete. You know, it was designed a long time ago. It has functionality. It makes assumptions about the data that comes in or the users that are no longer applicable. So we don't want to keep fixing it. And sometimes you have to do a clean rewrite and start from scratch. So the software becomes obsolete. There may be unfixable cybersecurity issues that can only be patched for so long, but ultimately we have to retire the software. Or it's being replaced by something newer, better. We have a new product on the market that's replacing our existing product, and the old version comes to an end. But this is a dramatically new version, so it's not really an update now. It's a new piece of software. And finally, the company might choose to exit this line of business. And in the medical world, this can happen either because the company is no longer interested or because it was acquired by a competitor, so the software could be retired, or it's being merged with another product. For whatever reason, the software lifecycle comes to an end. We will no longer support our software. So what does the process look like? How do we retire software? So what needs to happen at the end of life? You'll see end of life, or you'll see EOL. That means end of life. So this is a process that's called decommissioning, and as some of the regulatory documents top, this is the IMDRF speak here, we are stopping the maintenance, support, and distribution of the software in a controlled and managed fashion. Let me underline controlled and managed. We don't just call people and say, tomorrow the software is retiring, we're no longer supporting it. It has to be a slow and deliberate process with plenty of warning, like Microsoft is doing with Windows 10 in 5 years. We have to provide plenty of warning, as mentioned before, and we have to provide our customers support to both extract any valuable data from the system and to transition to a new system, and that is critical. So if there is data that's sitting on the system that needs to be removed, we help them get it out, and we help them move to a new system. And we have to ensure that data privacy is safeguarded. So if there are patient data on the hard drive, for example, of a device, when the device is retired, there should be procedures for wiping that disk clean, or maybe we take the workstation back. When the software is retired, it comes back to us, and we do the proper recycling procedure. So in every possible situation, we have to ensure that data privacy is safeguarded, anything valuable on the system is preserved, and we do it slowly and deliberately, so people know it's coming with plenty of warning. As a final slide, let's look at some of the IMDRF guidance on cybersecurity, and while this focuses on cybersecurity, it applies to all other kinds of software processes. So this is a flowchart. We'll zoom in a minute. At the top, it has the responsibilities of the medical device manufacturer, and at the bottom, it has the responsibilities and expectations of the customer. So let's walk through the steps. There are 4 parts of this life cycle. In the beginning, we're in development, and the manufacturer designs the devices under a secure development framework. For cybersecurity, the process starts, of course, from the beginning, and so we're developing the product. And development ends with commercial release. So at the point of commercial release, the medical device manufacturer communicates the end-of-life timeline for and support to customers with expected support provided until the day is reached. So now we end up a period called support from commercial release to end of life. And our customers know that this is coming, and they can depend on us being there for them for that period of time. The next step is what's called limited support. And this is an in-between stage where we only provide very minimal support, and the customer begins planning for activities at the end of support as communicated from the manufacturer. So we'll provide patches for the next 2 years, but no new features. That's typically actually how Microsoft does it for Windows. And then there is the end of support. The manufacturer no longer supports the software, and the provider, the customer now is fully responsible to transition from this piece of software to something else. So now, at the end of support, the whole weight of responsibility moves from the manufacturer to the customer, and we no longer provide support to the software. And so, if you remember nothing about this, is that retirement of software doesn't happen in one day. Plenty of warning, slow process. You handhold the customer to a particular point in time, but then at that point they're on their own. You cannot provide support forever, and healthcare systems need to be aware of that and plan for replacing software and not to hang on to software that appears to be working but is no longer supported. And this is beginning to become increasingly critical as we're seeing more and more cybersecurity incidents, and sometimes it's this older software that is targeted for this type of attacks. So this concludes this week 10 on validation, deployment, maintenance, and retirement. This brings us to the end of the software lifecycle. And if we were teaching this class 5 years ago, that would be the end of the class. However, the developments in artificial intelligence and machine learning mean that we need to revisit all of the steps within the context of the use of this technique. So rather than spread all the information about AI and ML throughout the class, we're going to focus and review this information in the next week's lectures. Thank you.